Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss sum and direct sum of submodules. Before that, we study here the theorems on modules, fundamental theorems on module. Yesterday we have seen, and today I will theorem, one more theorem. Let R be a ring such that I belongs to R. As R module M is cyclic if and only if M is isomorphic to R divides I for some left ideal I of R. Proof only part. Let M be cyclic. Hence M is equal to Rx for some x belongs to I am. Therefore M is equivalent to R by nx, where nx is a left ideal in R, and we get M is isomorphic to R by I. For left ideal I is equal to nxx in R. If part, let M is isomorphic to R by I, where I is a left ideal of R, I belongs to R. 1 plus I belongs to R by I. Further, R of 1 plus I is equal to R of 1 plus I, so that R belongs to R is equal to R plus I, so that R belongs to R is equal to R by I. This shows that R by I is a cyclic module generated by 1 plus I. As M is isomorphic to R by I and R by I is cyclic, we get M is cyclic module. Since isomorphic image of a cyclic module is a cyclic module. Next theorem, let R be a ring with unity I. Let M is not equal to 0, singleton 0 be an R module. Then prove that M is simple if and only if M is isomorphic to R by I, where I is maximal left ideal of R. Proof only part. Let M be a simple R module. As M is not equal to singleton 0, M is, we get M is equal to Rx for any x is not equal to 0 in M. As M is equal to Rx, a cyclic module, then M is isomorphic to R by I, where I is a left ideal of R. By the theorem, an isomorphic image of a simple module is a simple module. We get R by I is a simple module. Now, the submodules of R by I are of the form U by I, where U is a submodule of the module R containing I, but the submodule of an R module R are the left ideal in R. Hence, R by I being simple, there do not exist any left ideal in R containing I, but this shows that I is maximal left ideal in R. Hence, M is a simple module and M is not equal to singleton 0. Will imply that M is isomorphic to R by I, where I is a maximal ideal in R. If part, let M is isomorphic to R by I, where I is a maximal ideal left ideal in R, but this in turn will imply that there does not exist any proper ideal in R by I. Hence, R by I must be a simple R module, as M is isomorphic to R by I. We get M is a simple R module, since isomorphic image of a simple module is simple module. We come towards sum and direct product, direct sum of submodules. Here, in this topic, we study the sum of modules, direct sum of modules, free modules, and completely reducible modules. Now, definition of sum of submodules. Let M be an R module. Let M1, M2 K finite be R submodule of M. The submodule generated by union of I is equal to 1 to K, is called the sum of submodule Mj 1 less equal I less equal K, and is denoted by M1 plus M2 plus plus Mk, or simply summation of I is equal to 1 to K. Note that the submodule generated by union of I is equal to 1 to K, is the smallest R submodule of containing each 1 less equal I less equal K. Theorem for the submodule M1 M2 Mk of an R module M. Summation of I is equal to 1 to K is equal to x1 plus x2 plus xk, such that xi belongs to Mi. Proof. Let t is equal to x1 plus x2 plus xk for such that xi belongs to Mi. T is not equal to pi, as Mi is not equal to pi for each I. Let xy belongs to T, then x is equal to x1 plus x2 plus plus xk, y is equal to y1 plus y2 plus plus yk, where xi yi belongs to Mi for each I. Now x minus y is equal to x1 plus x2 plus plus xk minus y1 plus y2 plus plus yk is equal to x1 minus y1 plus x2 minus y2 plus plus xk minus yk, where xi yi belongs to Mi for all I, and M plus is an abelian group. But as Mi is a submodule of M, xi minus yi belongs to Mi for each I. Hence x minus y belongs to T. This shows that xy belongs to T, therefore x minus y belongs to T. Let x belongs to T and R belongs to R. Then x is equal to x1 plus x2 plus plus xn. Xi belongs to Mi for all I. Now Rx is equal to R into x1 plus x2 plus plus xn is equal to Rx1 plus Rx2 plus plus Rxn, as Mi is a R submodules of M, R belongs to R and Xi belongs to Mi. will imply that r dot xi belongs to Mn for each I. Hence, Rx belongs to T. Thus, for any R belongs to R and X belongs to T, such that Rx belongs to T, from 1 to 3, we get T is R submodule of M. T is R submodule of M. Let Xi belongs to Mi, then 0 belongs to Mi for each I, will imply xi is equal to 0 plus 0 plus dot dot plus xi plus 0 plus 0 dot dot. Hence, Yama is subset of T for each I 1 less equal I less equal k. Therefore, union of I is equal to 1 to k is subset of T. Next, let J be any other submodule of M containing union of I is equal to 1 to k. Then each Mi is subset of J. Let x belongs to T, then x is equal to x1 plus x2 plus dot dot plus xk, where xi belongs to Mi. For each I, 1 less equal I less equal k. As Yama is subset of J, we get xi belongs to J for each I 1 less equal I less equal k. Hence, J being a submodules of a module M, x1 plus x2 plus dot dot plus xn belongs to J. This shows that T is a subset of J. Thus, we have proved that T is a submodule of an R module containing R module M containing union of I is equal to 1 to k. Is the smallest submodule of M containing union of Mi. Hence, by definition, T is equal to summation of Mi, I is equal to 1 to k. Therefore, union or summation of Mi, I is equal to 1 to k is equal to x1 plus x2 plus dot dot plus xk. So that xi belongs to Mi, and this is proof.